Our video tutorial is about limits of exponential and trigonometric functions. Let us evaluate the limit of sine 7x over x as x approaches 0. We have here a theorem. The limit of sine x over x as x approaches 0 is equal to 1. So we have to multiply both numerator and denominator by a fraction equal to 1 so that we can make use of the theorem. That is 7 over 7. So distribute 7 with x, so that becomes, we have an expression sine 7x over 7x, which according to the theorem approaches a value of 1. So this is equal to 1. So as we evaluate the limit of this function, 7 times 1 or equal to 7. Next, evaluate the limit of x squared over sine 5x squared as x approaches 0. So we have to rearrange or multiply both numerator and denominator so that we can make use of this theorem on limit of sine x over x. We multiply both numerator and denominator by 1 over 5x squared, so that as we distribute 1 over 5x squared in the denominator, we have this expression sine 5x squared over 5x squared, which is according to the theorem equal to 1, and cancel out x squared in the numerator, and we have left with 1/5 over 1 or equal to 1 over 5. Next, evaluate the limit of x sine 2 over x as x approaches infinity with u equal to 2 over x, so that in this equation, if we solve for x, x is equal to 2 over u. As x approaches infinity, this denominator approaches a very big value. The fraction becomes 0. So u approaches a value 0. So our limit function this time is in terms of u. So limit of x is 2 over u. Sine of 2 over x is u as u approaches 0. We will rearrange the expression so that we have sine u over u, and making use of the theorem, this sine u over u is equal to 1. So as we evaluate the limit, this becomes 2 times 1 or equal to 2. Next, evaluate the limit of x squared minus 1 times sine of 1 over 1 plus x. So we have to multiply the whole expression by a fraction equivalent to 1 so that we can make use of the theorem on limit of sine x over x. So that is 1 over x plus 1. Distribute the numerator with this quantity and factor this at the same time. And the denominator we over sine. Cancel out common factor. So we have x minus 1 times this fraction, and according to the theorem, this is equal to 1. And as we evaluate the function, as x approaches negative infinity, this becomes negative infinity times 1. So this is negative infinity. So the limit of the function as x approaches negative infinity is negative infinity. Next, evaluate the limit of cosecant 8x tangent 5x as x approaches 0. We can express cosecant and tangent in terms of sine and cosine. So in this expression, or in this function, we can multiply the whole fraction by a fraction equivalent to 1 so that we can make use of this theorem. So that is 5 over 5x, because we have here 5x in sine. We have sine 5x and sine 8x, so we have 8 over 8x. This whole fraction is equivalent to 1. So distribute both numerator and denominator. So we have sine 5x over 5x and sine 8x over 8x. And as x approaches 0, this becomes cosine of 0. While this fractions is equal to 1, and this cosine 0 is 1. So as we simplify and evaluate the limit, this becomes 1 over 8 times 1 times 1, or 5 over 8. Next, evaluate the limit of cosine 2 pi over x cotangent to 3 pi over x as x approaches 3 from the right. So we can substitute x with 3 and cancel out 3 and express cotangent in terms of sine and cosine. Now let us determine the value of cosine of 2 pi over 3 from our circular function. 2 pi over 3 is equal to 120 degrees, and cosine of 120 degrees, its reference angle is 60 degrees, and it is found in the secant quadrant, and cosine in the secant quadrant is negative. Cosine of 60 degrees is 1/2, but it is in the secant quadrant, so it is negative 1/2. And cosine of pi, or cosine of 180 degrees, is equal to negative 1, because cosine in the secant quadrant is negative, and sine of pi, which is in the upper quadrant, sine in the upper quadrant is positive. It is approaching a value of 0 from a positive value. So this is negative 1/2, and cosine of pi is negative 1. The sine pi approaches a value 0 from a positive 1. So as we evaluate this fraction, this is negative infinity times negative 1/2. So negative times negative is positive. So the limit approaches positive infinity. Next, evaluate the limit of tangent squared 3x over x squared as x approaches 0. Again, we need to multiply the whole fraction so that we can make use of the theorem. So, at the same time, tangent is expressed in terms of sine and cosine. So we rearrange the fraction, distribute the x squared, and we need to have a coefficient of x squared so that we can make use of the theorem. So we multiply the whole expression by 3 squared over 3 squared. So that as we distribute 3 squared below sine, so here 3 squared, x squared here is x squared, sine squared, we remove the exponent outside. So this fraction is equal to 1 according to the theorem. Here, as x approaches 0, cosine of 0 is equal to 1. So we have this is equal to 1, and 3 squared over 1 squared. So as we evaluate, that is equal to 9. Next, evaluate the limit of e to the 2x plus e to the negative 2x all over e to the 2x minus e to the negative 2x. First, we need to change negative exponent to positive exponent by getting its inverse, and in its numerator and denominator, express it as a single fraction, and perform the operation of complex fraction and cancel out common factor. So we have here an expression. Factor out the highest exponent of e, that is e to the 4x, so that e to the 4x is distributed in its term. We go back to our original expression in numerator and denominator, and evaluate the fractional part as x approaches in positive infinity. So this becomes very large, and the whole fraction becomes 0, and cancel out common factor at the same time. So we are left with 1 over 1, or equal to 1. So the limit of this function as x approaches positive infinity is equal to 1. Next, evaluate the limit of 1 minus cosine x over tangent x as x approaches 0. So we have to rearrange the or introduce factor x, because if we apply these two fractions, we go back to the original one, so that we make use of another theorem on the limit of 1 minus cosine x over x as x approaches 0 is equal to 0. So we introduce x so that we come up with this expression and make use of this theorem. And express tangent x in terms of sine and cosine, and simplify this complex fraction. So we have x times sine x in the numerator, and separate this one. We have x over sine x, and evaluate the limit. According to this theorem, this is 0, and according to the previous theorem, this is 1, and as x is 0, this is equal to 1, so 0 times any number is equal to 0. Next, evaluate the limit of secant squared of 1 over x as x approaches positive infinity. Let us express secant squared or secant in terms of cosine. Okay. Then evaluate as x approaches infinity. So 1 over x as x approaches infinity becomes 0. Or we move the exponent to outside and evaluate this one. So this becomes cosine of 0. Cosine of 0 is equal to 1. So 1 square is equal to 1, or 1 over 1 is 1. So the limit of this function as x approaches positive infinity is equal to 1. Next, evaluate the limit of tangent x over 2x as x approaches 0. Now we can express tangent in terms of sine and cosine. Then rearrange so that x is over sine x times 1 over 2 cosine 2x, so that we can make use of the theorem of limit of sine x over x. And we evaluate this function as x approaches 0. This x becomes 0, so cosine of 0. While this fraction is equal to 1 according to the theorem, and cosine of 0 is equal to 1, so this is 1 times 1 over 2 times 1, so it is equal to 1/2. Next, evaluate the limit of sine to the fifth 2x over 4 x to the fifth as x approaches 0. So we have to multiply the whole fraction in such a way that we come up with something that we can make use of the theorem on the limit of sine x over x. So we multiply it with 2 cubed, so that 4 is 2 square. We have to multiply the denominator with 2 cubed and also with the numerator, so that we can have 2 to the fifth, because the exponent of sine here is 5. All exponent must be equal to 5. And this fraction, when we move out 5, the exponent 5 outside, it's here, times 2 cubed, which is 8. So this fraction, according to the theorem, is equal to 1. So we have, as we evaluate the limit of this function, this is 1 to the fifth times 8. So it is equal to 8. So that's enough. Thank you.